So far we've seen that the two postulates of special relativity, including this odd one that light always propagates at the same speed in whatever inertial reference frame you're looking at, has given us a lot of information already. It's told us that transverse dimensions are unaffected, and it's told us that time gets slower as you go into larger and larger velocities. Let's see what happens to length, and to do that we'll consider another device. This is going to be very much like the light clock, except it's going to have two arms now. So it's going to have a source and detector, and it's going to have two mirrors. And in the rest frame, both of these lengths are going to be the same, and so the pulses are going to come back and hit the source at exactly the same time. And because that's an event, that's going to be the same in all reference frames. So we're always going to have these pulses going away and coming back and landing together. So when this thing is in a new reference frame, when it's moving along, of course, this light in this top path is going to travel just like it did for the light clock where we were looking at the time dilation. It's going to travel in a kind of triangle instead, and so it's going to take longer. Where I've introduced this factor gamma, which is just this factor 1 on square root 1 minus v squared on c squared. So that's just the definition of gamma. And so t2 dash, which is going to be the time it takes to bounce off here, has to be the same. Because it was the same in one reference frame, it has to be the same in the other reference frame. Now in the rest frame, this axis, it just moves its length and then moves back its length, and it goes the same time for each. In a moving frame, however, when this thing is moving, when it emits, this mirror is going to have moved before that pulse can get there. And so the pulse going out is going to actually travel further. And then when it bounces back, this source is going to approach it, and so it's actually going to take less time coming back. So this is going to be broken into two pieces on the way back. And we can calculate exactly what these two times have to be. And what we've discovered is that the length, in order for that to all work, has to get shorter by the same factor gamma that the time got longer. And so what we've got here is length contraction. And again, there's nothing particularly special about that. So if I had a ruler next to it, the ruler would also have gotten shorter. And therefore, this is not just about the length of our physical device, this is about space itself. And so our x dash is going to be reduced by this factor of gamma. So putting all that together, we can find the exact relationship between the two reference frames. And that relationship is known as the Lorentz transforms. And as the name suggests, they were in fact invented by Lorentz some time before Einstein came along with relativity. And in fact, essentially what Einstein did was come up with a fundamental physical principle, reason why these things might occur. They were very controversial at the time because, of course, they say that two events that were simultaneous in one frame are not simultaneous in another frame. In other words, this idea of this sort of universal clock that's the same for everybody is completely broken. I must stress, of course, that both frames are right. There's no sense in which one frame is better than another. You just have to be careful when you translate from one to the other. And indeed, a lot of the tricks with doing relativity problems is to find a frame in which your calculation is easy.